Just some of the characteristics of glass. So float glass is very dangerous. So float is what comes out of the float plant. The glass is what we call float or annealed. It is very dangerous. If you break it, you can injure yourself severely. You can even die. And therefore, in most buildings where human impact is an issue, and for many other areas like fire or other reasons, glass needs to be safety. It needs to be a safety glass. So there are also different forms of safety glass. So here is a toughened safety glass, and I'm sure the majority of you would have seen it. So if I take this glass and I put it in a furnace and I temper it, so I bring it up to a temperature, I hold it there for a while for a process or a cycle, and then I rapidly cool it. It's a bit like the old blacksmith who was forges his metal red hot, and then he dips it in a bucket of cold water. It's effectively what we do with glass. That's how we temper it. That makes the glass stronger, and it changes its characteristics. So therefore, when it breaks into what these relatively safe granules. So small granules, and there is a requirement for a manufacturer like Viridian to abide by as far as toughened glass. So there are batch tests that we have to do, and a batch test will consist of smashing glass, but before we do, we put a tape over it so we don't lose the granules, and then we have to count how many granules are in a given area. Now the granules have to be of a particular number. It's no good having toughened glass and they break in pieces this big. So they have to be safe, they've got to be small, and you need to fit so many into the test little grid. Now I don't remember what the number is, but that's part of the production quality control. So that's toughened glass. Windscreens, years ago, front windscreens used to be made of toughened glass for you old people like myself. But now we use laminated glass, and that's what happens when laminated glass breaks. So maybe not that bad, and usually if you get a small stone on the laminated glass on your windscreen, you'll see a little chip, and in time it might start to propagate. And that might be the outer layer that starts to propagate that crack. If you throw something hard enough at a laminated glass, it'll do that. If you throw something even harder, it'll go through, depending on the type of interlayer that you use. Now, there are many, many different types of interlayers, and as an example, here's a polyvinyl butylate interlayer. Now, this interlayer is fairly soft. You can see it's malleable. I can move it. That's a bit of laminated glass. Here is another interlayer which I can't move. It's rigid. It's used for security applications. So you could throw a brick at that or try and hammer your way through it, and you won't get through. And this is how we can build security glass products or security applications. So that's laminated, and then we can combine the two. We can combine toughened and laminated, or heat strengthened and laminated. So when we combine the two, obviously we get a different level or different type of characteristics. So if we laminate two sheets of toughened glass together and they break, then the PVB interlayer that is in the middle, in a lot of cases, can hold that glass together. And we haven't got time in this forum to go through why we would do toughened laminates, but just quickly, toughened or heat strengthened laminates in some cases are used for structural assemblies like overhead glazing. That's just a schematic of an IGU, which I've shown you there. Now I want to talk about performance, and the VCA or the NCC now pretty much says that for commercial buildings our building needs to be energy efficient, and our domestic building, our residential building, our house, that also has to be pretty energy efficient. And there are minimum standards now for commercial class buildings and also domestic buildings. So in Victoria, we now have 6 staff. For the commercial buildings, we have what's called Section J of the BCA. Now that's a fairly simplistic and cheap method of assessing glass. It's not always the best. It's quite a rigid tool because it allows for quite a lot of error or safety margin, but commercial buildings and residential buildings have to have a minimum performance. So they've got to go through a method of assessment in order to determine what that window solution is. So many times I get inquiries from people saying, we're designing a building, what glass do we need? Well, I don't really know. I can tell you what I think is going to work, but unless you go through the process of assessment, we don't really know. And each building is quite specific. It's quite unique because it's unique to its own climate zone, orientation, and a whole lot of other factors. What governs the energy, the type of products that are energy efficient is, to one degree, it's the climate zones. So the climate zones down here, these blue areas, they're the cold areas. These white areas are the really cold areas. The areas up here, the 1, 2, 3s, very hot, and in the middle, the 4s and 5s, they're the mixed climate, the temperate climate. So if you are putting a house in 3 states and it's the same design, it's likely that your insulation product or your insulation requirement, as well as your glazing requirement, it may actually be different, and more so if it's a commercial building. So the climate zones of Australia are used in the tools, in the software tools that are used to assess houses or commercial buildings. This came out of the BCA some time ago, and it showed as far as energy use or the consumption of energy. If we have a look here, this purpley colour is the amount spent on heating. Right, so that's a heating colour. This colour here is cooling. Now, if you look at the impact of the climate zones, and we said that 1 to 3 are hot, so in the 1 to 3 climatic zones or climate zones of Australia where it's hot, we want to keep out that heat because it's undesirable in some instances, and so therefore we want to keep it out. So if you have a look at the 1 to 3s, which are this end of the scale, you'll notice that, say, Darwin or Brisbane, the majority of energy that's used is to cool, all right, and a very small amount to heat. If we go to the other extreme end and look at the colder climates, and we'll say, let's go to Hobart, the majority of energy used is to heat rather than to cool. So in these zones, heat gain is actually a desirable thing. We don't want to block heat coming into the building. We actually want that. And there are ways that we can manage all that, which we'll go through as we move through. And really, at the end of it, energy is very much related to comfort, because if we're not comfortable, it triggers a behaviour in us, and that behaviour can have an impact on that previous chart. So if we're uncomfortable and it's cold, we'll want to crank the heating up, and so that's a behaviour. It impacts on energy. If we're hot, we'll say we'll draw the blinds if possible. If there are external awnings, we'll want to draw them. But if it's still uncomfortable, we'll want to crank up the air conditioning. That behaviour also impacts on energy, and that goes back to that previous slide. So if we can live in buildings that are more comfortable, now there will never be such a thing as a totally comfortable building every day of the year, or very hard to do to find such a building. But if we can make buildings more comfortable, then our behaviours will change, and therefore the impact on energy use and the environment will be lesser. So I want to talk about how we look at glass when we're designing. So obviously orientation and exposure and climate zones are important. So orientation, exposure, so the direction of the house, and how much glass as a percentage or ratio of glass for per that facade. So if you have a west elevation and 90% of it is glass and there's no method of shading it, I don't think there's any glass that's going to make you totally comfortable in that application, unless you can create some kind of a horizontal or maybe some kind of a vertical shading device or some kind of a mechanised system that will shade during those really hot periods. All right, so that's really important. You can see here in the summertime, this is just a simple diagram of like a slatted louver roof. So when the sun's high in the sky, a design like that, now that can be timber, it can be metal, it can be some kind of element, but I've seen many designers use clever louver designs whereby when the sun is high in the sky, the sun basically goes through, it doesn't impact on the glass, it goes straight through, whereas when it's lower, the louvers can actually be angled to a position where they do protect the windows, so that sun can be reduced from penetrating through that window. So these kind of things can help dramatically, and this is where designers and architects should be looking at, and in some cases they work really well. Glass by itself, I mentioned earlier, is not actually a great product. So this is, as I said, this is a bit of 6mm clear glass. That glass in a standard aluminium frame in a house where the percentage of glass of the facade or of the building envelope represents about 10% of its building envelope would result in anything up to 60% loss of energy in winter and up to 90% gain in summer. Now, that's staggering when you think about only 10% of my envelope is resulting in that kind of energy loss. Next one. As an R value, and for those of you who understand R values, for quite a while designers and builders used to look at bulk insulation, and that was a smart thing to do because bulk insulation reduces conducted heat, so it insulates very well. But up until only, maybe 5 years ago, or maybe a little bit longer, maybe 7 years ago, windows was still going in as 4mm clear with aluminium frames. Now, if you look at some R values and look at, say, okay, R3.5, that's pretty good in the roof. R2 in the walls, that's pretty good. And an R.15 for that glass in an aluminium frame is shockingly bad. Why would you do it? Well, you can't do it anymore. And that's why the methods of assessment, so if it's a house in first rate 5 or maybe Accurate, is being used now to assess that building to ensure that in Victoria it is a 6-star. Now you may, if you've got a small percentage of glass, you might get away with that glass because there's not a lot of it. And your overall product, your home, still complies to 6-star. But if you've got very big, say a large home with a higher glass to wall ratio, it's probably very unlikely you're going to be able to use this product anymore. Right? And that's, ridiculous, numbers for what we've been pretty much using from the dawn of civilization up until about 10 years ago. All right? So it's pretty poor. Next one. So let's have a look at some definitions and go to the next slide. So when we're talking about heat gain and in a warm climate and during summer, we'd like to keep the heat out because we don't want to turn the air conditioning up. So heat coming in, that's basically from the sun, shortwave radiation, from the energy from the sun passing through the window. Now with clear glass, it just goes pretty much straight through. Clear glass does does absorb a little bit, probably about 20% just by itself. It probably restricts or is a barrier to about 20% of shortwave radiation. About 80% gets in. How do we measure heat gain? Well, we measure it with this factor here. This is a solar heat gain coefficient, and it measures how well a product blocks heat caused by the sun, by sunlight. And it is a total of the direct solar transmission and the part of the solar absorption dissipated inwards by radiation and convection. And the lower its number, the better the performance, the less heat it transmits. And I think, okay, so practical, I've lost some, ooh, okay. Practical solar heat gain coefficient is 0.7 to 0.8, you know, and down to 0.2. All right, now if we go to the next slide, here's a step-by-step improvement on solar heat gain coefficient. So where you need to block out more solar heat entering, then this is how you do it. So here's this clear glass at 0.73, tinted glass, and I've got some tinted products there, you know, of varying types. So that's a grey glass, so you can see the difference there. Okay, so tinted glass provides a moderate resistance. So that basically says that 50% of the heat is entering and about 50% is being rejected. Heavy tinted, so you can go quite heavy on tinted glass, or reflective glass can get down to, you know, 0.3. There are some products that will get down to 0.2. In this presentation, I'm not going to talk about light transmission, but for those of you that are interested, the lower you go down that scale of SHGC, the darker the glass is, therefore the less light transmission you have. So don't think that the lowest SHGC is always the best, because it isn't. And in the winter months, in some of the climate, in the colder climate zones, that is a desirable thing. You don't want to put the heavy tinted glass in a building in a climate zone 6 or even 7, and in the winter time struggle to get some heat through the glass. All right, so very careful selection of glass, and also by looking at its light transmission. Okay.
This is assuming direct sunlight on the window pane.
And also, it can also come in from, it can be absorbed and re-radiated from other, say, things like paving.
Sure. Right,
or another building. It might be another building next door, so you've got heat bouncing off that building as well. So you've got the direct, you've got the other radiated. Okay, click the next one, please. Next one, and one more, and one more. Okay, so now this is busy to read, but don't worry about it. I just wanted to point out here that we are talking about heat gain, or solar heat gain coefficient, and our clear glass, this is in fact a 3 mil glass. This rates up just over the 0.8. All right, so it's repelling about 15% of that solar heat entry, but it's allowing all of that in. Now, some people say, okay, well in that case we need double glazing. All right, so our double glazing is going to fix that. Well, here's a clear double glazed unit. All right, now purely because of the fact that we've got 2 sheets of clear glass, yes, it does do a little bit. So you are getting another, from 0.85 to 0.7. So you are getting another 10% maybe improvement, or 8% improvement. But that's not the solution. And you can see that the products that are down here, this is a double glazed unit. This is a low heat double glazed unit. But you can see the products that sit down at, say, the 0.5 and below range, they are all tinted. So there's a blue, there's a grey, there's a blue-green. All of these products here and here and here, they're all tinted. All right. Now, careful selection of tint is required, because again, you don't want to over-tint, thinking that that is everything. So here's our there's our clear glass. Here's a reasonably heavy tint. There's a light tint. All right. Now that is obviously going to have a higher solar heat gain coefficient. Keep in mind, higher is not better, but so higher number. So this one's the highest, then this one, then the dark one. So this might be the solution for a particular building. So careful consideration of the right product is really important. Next slide. So that was just a brief overview of heat gain, and we'll just talk now for a few minutes about heat loss. So in a cool climate zone, and we'll talk Victoria, we are a climate zone 6. We're a cold climate zone in comparison to the rest of the country. We want to keep the heat in the building. We want to reduce the amount of heat loss. If you recall a previous slide where I showed you the R value, now R I should have explained, R is the inverse of U, so we don't use R values for glass, but I just put that one up there so you could compare the R value of the glass to the wall insulation and the roof insulation. So that 0.17 R value is very poor. That would allow a huge amount of heat loss. And if you've ever spent time close to a clear window on a very cold night, and you haven't got a jumper on, you'll feel that cold on your back. You'll feel it through your bones. So that's, basically the heat is being drawn through the glass, goes from the hot side to the cold side. It goes through the glass. It's conducted through the glass, and also through the frame if it's aluminium. We'll talk about frames a little bit later on. Okay, so what is U value? Well, it measures how well a product prevents heat escaping. It's a measurement unit in watts per square metre per degree Celsius, and it's a measure of the rate of heat gain or loss through glazing due to the environmental differences. And the lower the number, the less heat flow. All right, so a lower U value is desirable in a cold climate zone. The lower the U value, the better the performance. And really in Victoria, it doesn't matter how low you go. If you go for the lowest, there is no detrimental impact because all you're doing is preventing heat loss. So that's actually a good thing. Click the next one. Okay, so now this is just an interesting slide because what we should be doing for cost purposes is we should be maxing out our insulation first. Now, why do that? Because insulation is cheap and glass is expensive. So where you can, and here are our star ratings. So you can achieve, 4, 5, up to 5 by using clever insulation. If you want to go beyond that and achieve your 6, these slides have come out really bad, I don't know why. Yeah, I'm just noticing some formatting issues here, but that's okay. So these are star ratings, so that's say 5 and that's 6 over here. So if you want to go, if you want to hit your 6 star, you do have to consider glass now. You do have to consider windows. This is why now windows are such, they are under the spotlight because we have maxed out. Within that wall design, you can't put 250 millimetres deep of bulk insulation in a 90 mil cavity. You can only work with what is there. So once you max that out, then the balance is the glass. And so this makes sense. And if you click on the next slide, you'll see that improved windows can get you right up to 8 star and sometimes even beyond. So U value, the practical range is between 6.2. That 6.2 represents this glass, clear glass in an aluminium frame. So that's the worst. You can't get any worse than that. In fact, 3 mil glass is probably a bit worse than that, but not much. Maybe 6.3 to 6.4. That's it. That's the worst. And the best is 1.8. Now 1.8 U value is something that you will probably get out of timber, you'll get it out of PVC, and you'll get it out of maybe not quite thermally broken. Some thermally broken frames, sorry? Out of, yeah. So there are some thermally broken suites in the market now, which will actually go below that. No. Local. We're not here to talk about companies, but there are some local companies that are now extruding and manufacturing here that can achieve 1.9, 2.1, 2.4 quite easily, 1.9 with a limited selection of frames. If you want to go below that, like to 1.5, you do have to look at Euro. Yeah. Next slide. Okay, so how do we improve on insulation? How do we improve on U value? Well, again, float glass here, we said, now, please don't get confused with the 6.2 that I showed in the previous slide. That 6.2 represented the glass in frame. This is just the glass U value, all right? And there is a difference, and I'm not going to go into that today because we haven't got time, but these are glass values. So float glass here, the actual glass itself, not including the frame, it's got a U value of 5.8. How we improve on that is we coat it with low E. So low E glass will then bring it into that range there, 4.1 to 3.6. We'll talk about low E in a sec. The next method of improving is double glazing with, and that brings us down to the 2.7. Again, this is only glass. We can then, for no extra cost, we put argon and we get a better improvement, or we do get an improvement there. We can then put low E into a double glaze unit and we bring it down to 1.9. We can then put argon at no extra cost and we bring it down to 1.5. And then we can look at other things like triple silver, with argon, and we can get that down to 1.3. So where this glass started off at a really poor number to begin with, we can now push it, significantly. And so again, this is what is available in the market. A glazing element, when we're talking about windows, we're not talking about the glass only. And so I'm not sure of your backgrounds, but if you are looking at windows, you must consider the impact of the frame. And the BCA or the NCC says that it's inclusive of the frame. So while glass is responsible for 90%, 85 to 90 something percent, the frame also impacts. So once you take a glass and put it in a frame, that does have an impact. And we'll show that in the next slide, I think. No, a couple more slides. So no, just go back if you can. Okay, so just a little bit about frames. Now, most commercial buildings, and for maintenance reasons, people like aluminium. Aluminium by itself is actually it's a very high conductor, therefore it's very poor from an energy loss point of view. But so aluminium frames are standard. Click on the next one. There are thermally broken aluminium frames, and that is the terminology that it is a material of low thermal conductivity that is inserted between the members of high conductivity in order to reduce the heat transfer. So you can read that, but this is an example of a thermally broken aluminium frame. So unlike normal extruded aluminium frames, which go from the outside to the inside in one extrusion, this is actually separated by this polyamide, like a PVC part section. All right. So the conductance or the energy transfer is significantly reduced with that. Now, if you're dealing in timber's a great product. PVC is also a great product, but hasn't really been developed yet in Australia. In my opinion, looks a bit ugly. But there are good products out there. Just if we glance at, let's say we pick our comfort plus clear. This is a clear low E glass. So this is okay. This is a clear low E. So this has a U value of 3.6. So it's much better than my clear glass that I was holding up before. So it has deposited on it a chemical vapor. It's an iron particle. It's embedded in the glass. It's integral to the glass, and I get a 3.6 U value. Now, if I put that in an aluminium frame, this is what happens to it. So note the impact of, this one here. Note the impact of the frame on the glass. All right, so where I start off with a really efficient glass, it's now gone to 4.7. Now, where I put it into a smaller aluminium frame, it's a little bit better because I have less aluminium and therefore I'm conducting much less. Right? I have less material to conduct through. So if I look at, say, a timber frame, in some cases I can actually be, negate or negative. So this is one that I've pulled from the market, which uses a clear low E, and it's 3.2. It's been rated actually better than the glass. All right. So generally, the timber frames will pretty much neutral. That they're basically neutral on the U value. So you don't lose U value like you do with aluminium in a timber frame. We won't spend too much time on the rest of that. Okay, and so here's just a quick chart. There's our single glaze, and this is inclusive of frame. So at about 6.5, that's single glazed in an aluminium frame. There's our double glazed aluminium. There's our double glazed argon with a thermal break. All right, so you can see how you can improve on heat loss or on U value by glass and selection of frame. Now, a little bit about the next one. Okay, now this is again our Dandenong float line. At this point here, this is where what we call our chemical vapor deposition happens. This is where low E's are applied. And basically the glass has come out of the hot end, it's still molten, and at that stage you can apply metals to it. And effectively a low E glass is like a deposit of metal on the surface of the glass. And I'm just conscious of the time. And I can use a conductance meter, and I can determine where the low E is. So the low E is on this side here, and it just so happens that that's a low E glass. That's the non-low E side. That's the non-low E side of that one. That happens to be a low E as well. So you can see it's basically just a sheet of metal in the same way that a sheet of metal reflects light, it reflects heat. Like if you ever held a sheet of metal up to the sun, it bounces the energy off. Well, that's effectively what low E is. The next, and it's done there, and that's what it looks like under severe magnification. So this is 50,000 times. That's the low E, and that's what it looks like face on. So it's basically applied to the glass, but each grain is smaller than the wavelength of visible light, and so you can still, light will still pass through it. All right. Keep moving. Keep moving. Just go back one. And no, keep going. Okay, don't worry. Keep going. There was a couple of little slideshows there, but something's happened to the formatting, which happens all the time actually. So look, we'll leave it. I'll leave my bit at that, unless you've got some questions.
Okay, what I'd like to do, maybe, is keep the questions until after Tony's. Tony has, he will be speaking. Tony Maham as a window manufacturer of high performance windows, so he'll be covering a lot of the same ground again from the point of view of a window manufacturer. And so maybe if we can keep the questions to the end, then both people will be able to join in the answering of those if we're comfortable with that.
Well, good evening everyone. Thanks for having me here. So, as a window manufacturer, we generally have the task of combining what we get on glass and the information we have, the drawing we get from an architect, and try to make it work. And we also generally also responsible to make a decision whether a window has then safety glass, tinted glass, or other things. So it can be a little bit challenging sometimes. Just go to the next one. So our company started in 1990. My background, you can hear from the accent, and I hope it's not too strong for you to understand what I'm saying. I'm originally from Austria. I worked in the industry over there. I've done a few different things. We came to Australia, and all I wanted to do was interior architecture. That's my background after I did joinery and window making, and make fine furniture, design it, and install. Very quickly I found out I couldn't make a living here. Nobody was prepared to pay the money it cost to build something nice. We went into the kitchen, and then after 2 years we wanted to build our own house, and I couldn't find any decent window. My wife threatened that we go back because she's not going to put up with the living conditions in a normal brick veneer home. So we thought, well, it might be a great idea to start making European type windows here. Thank God I didn't know then it would take 50 years for us to make a living out of window. But thank you very much. At the moment it goes very well. We're growing quite rapidly. We have an average growth of 25%. So obviously we're slowly starting to do the right thing, where the market is coming our way. So after what we heard from the glass, and I'm going to jump around a little bit, try to fill in a few gaps where windows are. You mentioned timber windows. He's right, generally timber windows, generally windows in Australia at the moment, most likely more third world country status than a first world country. It's especially timber windows are the same way manufacturers that were manufactured 100 years ago, just with a few more modern machinery, but not much has happened to it. It seems the new 6-star level and other things drag it along slowly. And we heard a lot about glass, but if you look at a thermal image of a building like you see down here, there's more to it. While you can fix the glass, you put solid glass in and you get a rating. But a window has this other thing that's called an opening sash. So you have all these gaps around the outside, and suddenly there's a different window I have here. And generally, if it's an old timber window or an aluminium window without a rubber seal or a rubber gasket around it, you could lose up to 2.5 to 3 cubic meters of air per linear meter of sash gaps. So it's massive. Generally, in Europe, when they have passive house studies, 60% of your energy loss in a building is draft. And the biggest loss of air happens around doors and windows. So you can generally fix the envelopes easily, but not the window. And every one of you knows, like, it always upsets me the last 20 years when I heard on the news, you have to put the heavy drapes around your windows. When we came and lived in the house and complained to the neighbors that the house was horribly cold, they said, yeah, you guys sit in front of the windows, you have always the curtain open. I said, to them, why didn't you put a brick wall there if you're not allowed to open it? And if you had, it's pumping. So there's this factor, and then slowly, obviously, the glass has come a long way. The big problem, so good for us, because it leaves us out there with a good product pretty much on our own, but the industry is not doing a heck of a lot there. They find, because they have still the old binding system, they have problems applying pressure to the rubber seals. So if you have negative pressure or positive pressure out there in the environment, in the weather, it affects and either sucks the out or lets air through. So draft, as you can see here, is a very, very big factor. And I must say, the standard is coming along, has come a long way. The standard in Australia is actually not bad. The big problem is nobody really polices it. Try to change it. I've got like before also this climate chat, so I won't say anything to that. But you also, a lot of you have seen all this star rating. With our windows we get lots of stars. They have to extend the stars because we didn't fit in there initially. But I'm actually really say that's too much dumbing down. I always say yes, it is a bit like what you have on a fridge and on other things, but it does give the picture. And I always say, actually, the people are much smarter. And when you look at the window rating, please look at the U value and look at the solar heat gain coefficient and the numbers itself. They tell you a lot more than the stars, because they can be a little bit deceiving. The other thing is also there's an air infiltration factor when you go onto the VS rating website, website, which tells you how much air is let into the window. As long as some companies put now fixed windows in here, of course they're airtight and they're pretty good performance forming. So look at these numbers. That tells you a lot more than the stars. The stars can be manipulated, and we always have issues that some products get a lot of stars, although the U value is actually not that great. The frame has a big impact, and like I'm certainly not talking here from a position of somebody who has an extremely sophisticated frame. We're not talking here your normal double hung window, your awning window, or a casement window where you have a flimsy timber frame or worse, or an aluminium frame. So the frame outperforms a standard clear double glazed window a fair bit. And then with the right glazing. Glazing also I can get in Europe, and you guys don't provide it for me to my frustration, like these heat mirrors. At the moment I can get glass in Australia where I can get a U value of 0.9 on a window. So you can bring it down that far. For you guys who might sometimes look into European websites or German websites, you have to be a little bit careful. The German website gives you U values of 0.5, 0.6. The U value calculated in Germany is different than out here. So like when we had ours tested up to, I think it was 2000, we had a different U value system and everything got reevaluated. And now a U value of 0.9 would be around about equivalent to a Central European rating of a U value of 0.56. It's just the calculation is slightly different. But yes, we can now manufacture in Australia with locally available glass down to about 0.9, but mainly achieve that ones who have a superior, stronger frame. I also need a stronger frame to accommodate all the hardware to hold the sash in place, as well as accommodate for one or on higher performance. We have 2 levels of rubber seals and all that sort of thing, and obviously a triple glazed unit. I spoke before already a bit of air infiltration. Like air infiltration should be around about 0.05. Very often on the VS rating you see some products that have 5 written there, which means 5, they never build up any pressure in the test facility, and sort of got this number 5 is the highest you can go sort of thing, which means it's as drafty as it can be. While you have here a picture that's of a PVC window, generally on frames you have a different frame combination, and I might say on a bar framing wise is PVC and timber. There's not much variation if it's a European type profile. Certainly if you go then down to a timber frame, general awning or double hung window, the frame is half the thickness. Is not a great deal different. The biggest problem with timber window is then the air infiltration factor on a poorly designed or manufactured timber frame. So generally with clear double glazed window and an airtight frame, and a frame that is about 70 millimeter thick, you get a minimum of 2.2. It's about 2.1 with argon filled double glazing. So the air infiltration is a very, very important factor. Another thing for windows, so the AWA test and all the window tested should have a performance label on it. First thing, that it's tested and complies with the Australian standard, and it also should give you a design performance, as a structural, how how strong the wind can be before the window falls apart or bends, and water resistance, that's at water pressure, that's 150 Pascal, water enters through the sash, so it basically starts to leak. The minimum performance here in Victoria is is 150 Pascal water penetration, and like with our windows, we have gone up to close to hurricane level before we got any drop of water through the frame. But when you get windows, you should look for a label like that. Again, unfortunately, a lot of the industry and the biggest performance, biggest thing in the manufacturers is timber windows, because their windows most likely would never make it through the test. So they build a generic Australia window, tested, I don't know where, and when you have this generic Australian timber window, you don't need to go testing, you just have your body sample. Generally, these window manufacturers use the ratings the glass manufacturer supplies and writes out the certificate of compliance. And fortunately for the industry, the window inspectors generally don't check and are not obliged to check. So they take the certificate of compliance and put it in. So you might get a timber or aluminium window that has a glass in there that very well may perform a U value of 1.8, but the window itself could be 2.7, and God help, it could be even worse than that. So it's going to be up to the consumer to make, to do the homework to make sure to get the right windows supplied. And that's that bad thing in the market. Orientation, as we heard before, very, very important. Much more important than what window you use initially. Get the orientation of the house right, get all the other materials right, and then the last thing, you look at windows. And it's a cultural thing here. Like very often here, windows in Europe are rather smaller than out here. Certainly it's one reason that like we heard before, windows and glass is a very bad performer. Single glazing, I always call it just camping. It keeps the water out and it keeps the wind up, but it doesn't do much else. And you really have to go in a high performance glass before you get anywhere. So as we heard before, fix the bulk insulation or other insulation first, get the walls, get the orientation right, and then select the right windows. I see drawings with huge areas of glass. And then I ask, what do you see through the window? I generally ask when it comes from suburbia somewhere, and they said, oh, the neighbor fence. I said, why do you have these big windows? He hadn't thought about it. Generally, the planner might put it in. Historically, and some old-fashioned builder told me once, it started sort of in the 50s. Somebody found out if you put a lot of windows into your house, preferably floor to ceiling with a bit of a lintel over the top of it, you can bring the square meter reach of your bricks down, and windows, cheap aluminium windows, be a fraction of a brick wall. So if you do that, if you have a stump wall of brick, you have a big window and so on, you can build quite a cheap house. Nobody can live in it. And I've been to some of the houses, and I recently was one down in near, not very far towards Brighton, built in the 60s. I would say 80% of the building was glass. It was a very modern building then, but because it was all single glazing, 4mm, maybe some laminated as safety glass, if that, yeah, people said, you know, in winter, as soon as the sun goes down, it just gets bitterly cold inside, and you just have to pump energy in. And in winter, in summer, it gets boiling hot. And the temperature generally follows the outside temperature in a 1 hour delay. So, and generally when I get to a house like that, all I can say, you most likely can't or wouldn't want to afford what it costs to replace all that glazed area to get it to a standard where you feel comfortable. Because when you have that much glass, even if I had to go in with triple glazing, 2 heat curtains, which are not available in Australia as yet, I might get up to a U value of 0.9, 0.8. It just would get too expensive for starters, and also the R value in comparison still would be only an R value of 1, which would be generally unacceptable in a brick model, so a brick veneer wall. Soil rotation is quite important, and I would say if you have to have west facing, because sometimes you can't prevent them in the design, first stage would be try to have external shading. Your tree is one option, the old-fashioned shutters, where it's casement file shutters or external venetian blinds, and there's all sort of things around nowadays. Veranda, of course, do that.